Hello students, in this video we'll prove Goursat's theorem, which is the first step to proving the Cauchy integral formula. So this is Goursat's theorem. It states the following. It says let F map omega into C be holomorphic on the domain omega, and we want omega to have some nice geometric properties, right? So we want omega in some sense to be an open set, so I want it to be open and just connected. We can sort of loosen some of these restrictions later on, but for the sake of argument, let's just look at this case when the omega is open and connected, right? And then I want to be able to put a triangle into omega. Now, of course, if it's an open set, I can always find some small enough triangle, right? So what I'm going to do is I'm going to say, okay, well, there's a triangle over here that's in omega t, right? So t is a triangle. In omega, in the interior omega. And what the Goursat theorem states is the following. It says if I give you a triangle inside omega, and it's such that the triangle is entirely contained in omega, then the integral over that triangle, which is a closed curve now, of f of z dz is equal to 0. So if I integrate over a closed triangle, I get 0, okay, for a holomorphic function. Okay, excellent. So how are we going to approach this problem? So it's a beautiful result. And so what I'm going to do is I'm just going to draw a triangle over here like this. There's a triangle T. And it's oriented, let's orient it counterclockwise, like so. Oriented counterclockwise. Excellent. And so now what I want to do is the following. So what I'd like to do is I'd like to take this triangle, and so here's the first step of the proof. So the proof goes as follows. Let's do proof. Divide T into 4 smaller triangles. By bisecting the midpoints via bisection. That's an easy enough idea. And so what I'm going to do over here is I'm going to take the midpoints of the sides of the triangle. And if I do this, it's clear to see that we get 4 triangles, right? And now let's think about the orientation of these triangles, right? So in other words, if I want to add these triangles into the overall picture, I'm going to call this triangle over here T1, this one T2, this one T3, and this one T4, okay? Now, how will I orient these new triangles? Well, T1 has this orientation, so the orientation T1 wants to go this way, right? And then this way, and then this way to be anti-clockwise, okay? So that orients T1, okay? So notice that T1 has 2 orientations that coincide with the initial orientation of the triangle to start with. How should T3 be oriented? T should be oriented like this. Great. How should T4 be oriented? Like this. And then how should T2 be oriented, this middle triangle over here? T2 should be oriented anti-clockwise over here, right? So it should be oriented like this. Oh, those arrows pointing in opposite directions. Then like this. Oh, those arrows are pointing in opposite directions. And like this, those arrows are pointing in opposite directions. So these opposite pointing orientations completely cancel out. In other words, if I want to integrate over this triangle T over here, I can integrate over T1, T2, T3, and T4, because T4, T3, and T1 contain parts of the orientation of the original triangle, and the orientation of T2, it completely cancels out, right? So the T2 contribution, the T2 orientations, the middle orientations, are opposite, so they cancel. This is a very important, it may seem very simple. I just drew the arrows like, oh, look, the arrows are pointing in opposite directions, they cancel out. We're going to see the same trick in the Cauchy theorem and the Cauchy integral formula. We're going to see this when we do any application of Cauchy where we're trying to compute residues of things. The orientation plays an essential role, and keeping track of the orientation will get things to balance out in typically the right way. So it may seem like a slightly nuanced point, but keeping track of the orientations and figuring out where orientations cancel is a very important idea. Great. So what does this tell me? This tells me, therefore, that the integral over t, the absolute value of the integral over t, f of z dz, is equal to the absolute value of the sum. J goes from 1 up to 4. The integral over these new triangles tj, f of z dz. okay? So what I have over here is I have the overall size of this integral in absolute value is the sum of these, the absolute value, the sum of these four things, which means that one of these four integrals over here has to be 4 times that one of them has to be at least that much, at least the total integral over here. So there is one of these four, there is a T1, and this T1 triangle is coming from the T1, T2, T3, T4 set of triangles, that first generation, such that the integral over T of f of z dz is less than or equal to 4, the absolute value of the integral over T1 f of z dz. Okay, that's just a standard observation about absolute values, right? So think about this for a second. If I gave you some numbers over here, if I said that the modulus of z was actually the modulus of a plus b plus c plus d, all four of those numbers, a, b, c, and d modulus cannot all be strictly less than a quarter of z, because if they were all strictly less than a quarter of z, that would say the absolute value of z was strictly bigger than the absolute value of all four of them, right? So in other words, I'm just using this very simple idea over here that if you have the absolute value of a complex number, the modulus of a complex number, and I express it as the modulus of the sum of 4 complex numbers, at least one of those complex numbers, if I multiply by 4, has to exceed or be equal to the overall modulus of z. That's all I'm saying over here. So it's just a very simple geometric argument, okay? Now, what do I know about this T1 over here? So here's where the notation comes in. Let's let P0 be the perimeter of T. The original triangle, and D0 be initial diameter, be the diameter of T, okay? Of course, what's diameter? So recall, the diameter of a set E is what? Is just the supremum over all x and y and e of the absolute value of x minus y. That's what the diameter of a set is, okay? In other words, if you don't like supremum, it's the maximal distance between 2 points in the set. That's all, right? Okay. So in other words, the diameter of a circle is its diameter, right? So in other words, there's a generalization of the idea of diameter from a circle to an arbitrary set. Okay. Good. Then what's the relationship between and then similarly, P1 and D1 are the same quantities for T1. Okay? Then what can we see from this? We can see that the relationship is that P1 is 2 to the negative 1 P0. I'm bisecting it, so the perimeter is cut in half. And the same thing is true with the diameter. Since I'm cutting this uniformly, I get the same thing for the diameter. So D1 is equal to 2 to the negative 1 D, of course. So D0. Okay? Excellent. And now we have the structure of the theorem in place, right? So in other words, now what will I do with this T1? We're going to do the same procedure to T1. Do the same procedure. To T1 to get T2, etc., and then induction, and then induct. Okay? And then we're going to get a sequence of triangles, T1, and then which contains T2, T2, T3, etc. Now here's the salient features of these things. We get the following estimates. What estimates do we need over here? So the first estimate we get is that the integral over T of f of z dz. Well, every time I go down a generation from T, going from T to T1, I got a factor of 4. Going from T1 to T2, I'll get another factor of 4. Going from T2 to T3, I'll get another factor of 4. So if I do this n times, I'll have 4 to the power n, then the integral over Tn f of z dz. Okay? And then we'll have what? What relationship do we have for these diameters over here? The diameter relations would be the following. We'll have that dn is 2 to the negative n d0, and pn is 2 to the negative n p0. Okay? Now, what's the point over here? The point over here is that if I look at the intersection of all, what's going to happen? So if I look at the intersection of all these triangles, so the intersection of the interior of TK with TK itself, if I look at all these triangles are getting smaller and smaller and smaller and smaller. It's a nested family of compact sets. That's nested family of compacts. Okay, and that nested family of compact sets by the Cantor theorem converges to a single point in the metric space. Call it Z0. Okay. So imagine the same situation for circles, right? If I take the unit circle and I look at the circle of radius n minus 1 over n, n minus 2 over n, n minus 3 over n, n minus 4 over n, and I take those circles, they're all collapsing to the origin. The same is true for triangles. If I give you a triangle, then I give you a smaller triangle inside that triangle, a smaller triangle inside that triangle, now it's just bouncing around a little bit, but it's going to converge uniquely to a point Z0. Now what we'll do is we'll write this over here. Now that's the essential part of the argument. So this is going to be what? This is going to be 4 to the power n, and then integral over Tn. Now I will Taylor expand f's into holomorphic. This is going to be f of Z0 plus f prime of Z0, z minus Z0, and then plus a function over here, phi of z, z minus Z0, dz. Now, look at these terms over here. These terms over here, f of Z0 and f prime of Z0, z minus Z0, that's a linear function. We know that linear functions have primitives. So these terms over here are just going to integrate to nothing around that triangle in the nth generation, right? And then what we'll be left with is we're going to be left with 4 to the power n, absolute value over Tn, and then this function phi of z, z minus Z0. dz. Okay. Now there are 3 terms to estimate over here. Now we're done. Okay. I'm going to put the absolute value on the inside. So this is less than or equal to 4 to the power n. Now I'm going to use the length of Tn is the perimeter, so that's going to be Pn. That's going to be the perimeter Pn. Then z minus Z0 is no more than the diameter because z is on the triangle and Z0 is inside, so that's less than the diameter of that triangle. So that gives me a dn. And then what? And then the supremum or the maximum on Tn of this phi of z. On Tn of phi of z. That's perfect spacing because let's think about what's going to happen now to this estimate over here. So I have a 4 to the n. I have a Pn and then a Dn, okay? So what are the Pn is going to be what? The Pn is 2 to the negative n P0. And then the Dn is 2 to the negative n D0. So I have a 2 to the negative n, 2 to the negative n. So this and this and this will cancel out and just give me a what? A D0 and a P0 times the maximum of this function phi on Dn. Now, since f is differentiable at Z0, this function phi of z has to tend to 0 as z goes to Z0. So for this function phi of z is tending to 0. So let's do it over here. So phi of z tends to 0 as z approaches Z0 over here, right? And now as n gets very, 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 very large, what's happening to z and Z0? As n gets very large, this collection of Tn's is collapsing to Z0. So as n goes to infinity, as I take the limit over here of this thing as n goes to infinity, what happens? It's the limit as this thing over here as n goes to infinity, and that goes to what? That goes to 0 as n goes to infinity, right? So I've just shown that the absolute value over t of f of z dz, an absolute value, goes to 0 as n goes to infinity. This left-hand side is independent of n, has nothing to do with n. So I can let n go to infinity over here, get 0, and that forces the integral over t of f of z dz to be equal to 0. Now the important feature of this last step is that, what am I using over here? I'm using the fact that linear functions have primitives. If you have a primitive over a closed curve, you're 0. We've already proved that. Primitive over a closed curve gives you 0. That's very similar to Calc 3. If I have a conservative vector field and I integrate it over a closed curve, I get 0. That's one of the fundamental ideas. The same thing is true for functions of a complex variable. Then, what does it mean to be differentiable? As I let z go to z0, if I was to divide by z0, this term, if I divide by z0 over here, like f of z minus f of z0, f of z minus f of z0 over z minus z0, it has to converge to f prime of z0, which means that this function phi, by definition of differentiability, has to converge to 0 by definition of differentiability, right? So this over here is exactly, this statement over here is exactly the same as saying that f is what? F is holomorphic on that domain. In particular, it's holomorphic at the point z0, which is inside this domain. Good. Then the final piece is that you have 4 to the n pieces, and then you have n of the perimeters, but the nth perimeter is 2 to the negative n, and then the nth diameter is also 2 to the negative n times these constants over here. Those constants don't change the fact that as n goes to infinity, this expression over here, the maximum of phi of z, gets closer and closer and closer and closer and closer to the value phi of z0, and I know that this thing has to tend to 0 as z goes to z0, which means that that expression is tending to 0. So that shows me that the integral over a closed triangle that's oriented of a holomorphic function defined on a set larger than that triangle, an open set larger than that triangle containing it, must be equal to 0, and that is the Goursat theorem. The Goursat theorem now is a very, very powerful theorem because you might think of some other geometric shapes I can do this on. So a great exercise is to take this argument I've just done here and do the same exact argument for a rectangle, right? The same exact argument is going to work for a rectangle, and that will help you get one extra level of understanding for why the Goursat theorem is true. So my recommendation to you is draw a rectangle, and now with a rectangle, you can just cut it in half and cut it in half, and you have 4 other rectangles. Same sort of reasoning applies, right? And moreover, what's the relationship between the diameter of the children of those rectangles and the overall rectangle? It's a half and it's a half. So in other words, the same scaling works. So you'll pick, of those generations, you'll pick one of those 4, and of those 4, the diameter scales by a half and the perimeter scales by a half, and that allows me to use the same exact arguments to prove that the same result is true for rectangles, which we'll use in future videos. Thank you very much.